welcome everyone to the AI for Autonomous Vehicles workshop. Our guest today is Daniel Sikar. You probably already know him from his previous sessions. He has done 3 sessions with us right now, so you should be quite familiar with him. We'll jump straight to the presentation, and I guess Daniel will take a lead from here. So, after Daniel.
Actually, I think Ben wanted to.
Oh, sorry, I'll just mention quickly that we have the society elections that have opened today. So if you'd like to put yourself forward for president or communications officer or finance officer in the society, then you can nominate yourself online, and I'll put the link in the chat in a second. And that means you get to be involved in running these events. And it's a good thing to put on your CV as well. So if you want to chat about that, just message me on Zoom or WhatsApp. But yeah, apart from that, we can get started.
Okay, so can you hear me, Ben, Max?
Yep, sound good.
Cool. All right. So thanks, guys, for turning up. And today we're going to talk about artificial intelligence for autonomous vehicles. So predicting steering angles from images. So given an image, what is the steering angle this autonomous vehicle should be steering at? So we're going to use convolutional neural networks like we have done in our previous 2 workshops. And so it's one approach, and it was the topic of my MSc dissertation, evaluation of self-driving cars using CNNs in the rain. Right at this moment, Ben, could you please post the link for this GitHub page in the chat so everyone could have access to this page? And so,
yep, it's in there now.
Cool. So if everyone who's joined, if you could please click that link, and that would bring you to the same page you should be seeing on your screen, which is a GitHub page with the repository for our workshop today. Right. So this was then based on my MSc dissertation, and the title was Evaluation of Self-Driving Cars Using Convolutional Neural Networks in the Rain. And in the case of the dissertation, there was some added noise, rain-like patterns in the images to see how those models behaved. We're not going to do that in this case. So, and also we are going to use a pre-trained model. So a model that has been trained already. Okay, so let's look at what we have here. We have a circuit that looks like this one that we see on this image on the right, and it was generated with the Unity game engine. So of which there are quite a few around. And like Unity is a big game in that space, a big name. Unreal Engine is another big name in that space. So this then generated a data set for me, the training data set. And they consisted of images, like an image like this one, like these 3 images, plus a set of labels. So it's a labeled data set. So it's a supervised learning task. If you have been taking like neurocomputing or machine learning, you should be familiar with that term, supervised learning. So we have our examples, which are images, and our labels, which are our steering angles. And then in this case, the vehicle that drove around this track was using a PID algorithm. So that stands for proportional integral derivative, and it's used for industrial automation processes such as temperature control. So if it's too cold, the temperature starts shooting up, but then it overshoots and the PID corrects it, start going down again. So it keeps adjusting the temperature up and down to keep to the desired temperature. So that was used to drive this around the track to get the data. So if we look at that data and we plot all the steering angles from one lap, which are about 1,400 images, this is what we get. So we can see it's kind of a normal distribution, but there's more data on the positive side because we're going clockwise and returning right most of the time. So there are 4 right turns and 1 left turn, this long, gentle left turn here. And we can see that by the plotted values. So we start, the y-axis is inverted, by the way. So if you tilt your head right, kind of the direction that line is going should correspond with the way the steering wheel is going, right and left. So we start with a right turn up here, and then there's a straight, there's another right turn, which is that second one, there's a long left turn. So it's on this plateau at -5 degrees for a while, which is that long left here. Then there's a very sharp, like over 90-degree right turn here, which is that dip. And then there's a 90-degree turn, another dip, and then the straight to the finish line. So that's the data set we have. And the data is normalized. So the output from Unity is normalized. The maximum steering angle is 25 degrees. The minimum steering angle is -25 degrees, but we divide those values by 25 to make the training easier. And the key word here to remember for future reference is vanishing gradients, because if you're dealing with larger values, say if we were using -25 and 25 as labels, it could lead to problems with vanishing gradients. So that's one of the reasons that with this kind of problem, regression problem, you do tend to normalize the output. So the outputs would be within a smaller range, in this case, between -1 and 1. Okay, so we'll look at some images here. This image is number 100. So it's, and if we look at this plot, 100 is between those 2 points, 0 and 200. I'm going to zoom in a little bit. And so it's on a straight, and it says, yeah, the steering angle here is practically 0. And if we multiply by 25, it is still practically 0. So it's going straight. And then if we look at image 200, so if we look at 200 here, it's at this point, it would be turning right. So it's on that right turn, and the steering angle here is saying it's 12, almost 13 degrees. So +13 is doing a right turn. And if we look at image 600, which if we look at the plot, 600 is along this plateau here. So it should be along this long, gentle left turn. We have a negative steering angle of -3 approximately degrees. So we're steering left. That's what those figures are telling us, right? So now we can jump to our notebook. So if we click on this button here, open in Colab, all being well, we will land on this page. So let's, could someone confirm in the chat that we're on this page?
Yeah, it looks like it works.
Cool. Okay, so if my internet connection drops out, Ben or Max both will take over and we'll carry on running the notebook. But basically, it's just a question of running every cell sequentially from 1 to 24. We have 24 cells to run. So if you're doing the MSc Data Science, you're probably very familiar with Jupyter Notebook and Google Colab. If you're not familiar, if that doesn't mean anything, Google Colab, which is this icon CO up here, or Jupyter Notebooks, which is the actual platform we're running this code on. What we have two types of cells here. One is a text cell, which contains text. So that's a text cell, and that's a text cell. And we have a code cell, which are these ones. And we will be running the code cell. So to run the code cell, we click on the code cell, and then you can either click the play button or Control Enter, as shown on this little toast that popped up on the screen. Okay, so what are our learning objectives? To gain familiarity with this environment, if you haven't, to load a pre-trained model, make predictions and assess the results. So a model that has been trained already, and then to train a model. So this was not on the script, but I had to do it in the end because my model didn't work very well on Google Colab. So here we go. So the first one we run is the cell up here. There are a number of commands and comments which are preceded by the hash symbol or the pound symbol, as it's also known. So everything that starts with a pound is a comment. Some are proper comments, so it's not code. It's like just a comment about what the next commented command will do. The only one I'm going to run here that is uncommented is !ls. The exclamation mark is an indication that the following should be run on the actual virtual machine that we're on. So it's a command that should be run. Google sign-in required. Damn. Okay. Ben, can you confirm if you leave page, we're able to,
So yeah, for me, it just asked for the same verification code that we had in the previous notebooks.
Okay, cool. Right, so if anyone is not signed in, this is a good time to sign in. And then at this point, once you're signed into Google, and sorry, you do need I imagine a Google account. So I should have made a note of that. Take it for granted. A note is being loaded from GitHub. So there's a warning there. It's being loaded from GitHub. Google doesn't know who authored this. And are you sure you trust it? So, well, I clicked yes. I wrote this and it's not malicious code. So I promise. So when we run this guy, everything is commented apart from that one. And what this command is saying is list everything that is that you can see on that command on the virtual machine. And it says, yeah, there's a directory there called sample data. And if we wanted to look into that directory, we could type here sample data and run this again. I'm going to click Control Enter. And it says, those are the bits that are in your sample data. So we're not going to use this, by the way, but this is, you get this by default. So like the famous MNIST data set, or at least comma separated values file describing it is in this sample data directory, right? Next thing, we're going to get the data. So if you run this cell, it's going to ask us for, in case you haven't authenticated, to authenticate, which I'm going to do now. So we click this link. And so as you run that cell, all these bits show up. You click on that link and I choose an account. This page shows up. And here we click allow. And when we click allow, it gives us a code. So I'm going to copy it by clicking this icon here. I'm going to go back to the tab where the notebook is, and I'm going to paste it in this text box here and press enter. So that's it. Once you're authenticated, that spinner keeps spinning. It downloads the data, which is on Google Drive. So in future, if you want to run your own workshops, or if you're doing some coursework, you can follow this recipe here if you're stuck. If you haven't worked it out in another way, maybe, or maybe there are other ways of doing it. This is the way I did it. So I upload the file to Google Drive. Say I want to share this with everyone. It gives me a link. I get the ID out of the link, which is over there. I paste the ID in here and download the data. Now I know the name of the file I uploaded, and so I just put that in here. And that's something you need to connect yourself in case you want to follow this recipe to get your data into your Colab notebook. Okay, so now we should have the data. So around step 3, we're going to decompress the data. And what we're going to do is we just need to run this cell. And what it's doing is saying, I'm going to run exclamation marks. I'm going to run a command, which is tar, which is an archiving utility. And we're giving it the switches XVF, which stands for expand verbose file. And we want to decompress the file we've just downloaded, which is our data set. And all being well, you should have a long list of files there now. So Ben, could you confirm that, or could someone confirm you've got those files? Or are we okay?
Yeah, it's working for me so far. Yep.
Cool. Max, all good?
Yeah, all good.
Okay, cool. So next thing, we are going to look at what is, we're going to look at a label. So what we're saying here is exclamation mark again. This is the concatenate command, which is basically going to pick the contents of a file and output it to standard output, which is the shell in this case. And we want to see the contents of this file, record_100.json. This is a label, and it's a label for the corresponding image 100_cam, etc.jpg. So if you run that guy, it says, right, these are the contents of the file. It's a JSON file, as the file extension indicates, and it has a few attributes. The attribute we are interested in is user angle. And it says here, well, the user angle, and this is a normalized value, remember, it was divided by 25 at the time Unity output this file. And it is close to going straight here. So it's very close to 0, this steering angle. So next thing, we're going to plot the steering angles from this data set. We're going to get all these steering angles in these files and plot them. So we run this guy here, this next cell, and it's going to import a few libraries. So JSON to deal with the JSON files, NumPy, a numerical library from Python, Matplotlib, a plotting library, a statistical library, another plotting library, a OS library for access to the operating system, and a match, FN match. And if you hover over them, you get a description of what each of those modules does. So there are a few functions defined, and then we run a set of scripts and we get this plot, which is the same plot we have here. So meaning, okay, so up to here, all good. Those plots correspond to what we've seen before. So we're in sync with what with the data. So next thing, we run this to find out what versions we have. So we're importing the Keras library, the TensorFlow library, so machine learning libraries, and we want to know what version of Python we're running. And it tells us, right, you're running Python 3.7, TensorFlow, and Keras versions. And there they are. And it's important to keep this in mind, because if you're training in one place and deploying these models in another, it's important to keep track of what these versions are. In this case, we're going to load a pre-trained. Now we go on. This was an aside, right? Something to keep in mind for future reference. Now we go on and run cell 7. So I'm just going to comment this guy out as well, this first line, and I'm going to run everything together. So I'm going to list the models, and at the same time, I'm going to load these two. And it's the first outline of the output are the contents of this models directory that came down in that compressed file we decompressed a few steps back. So these are the two pre-trained models we have. And then we get a warning, which I'm not going to go into. But okay, so now we can actually show some, now that we loaded the model, we can actually make a prediction, and that is going to happen on this line down here. So we're going to import the computer vision library, the matplotlib, and two libraries from matplotlib, PLT and MPIMG. And we use this, we do this because then we can refer to these submodules, so to speak, directly by PLT and MPIG. Otherwise, you end up with loads of dots and names, and it's a bit more awkward to write the code than to read it. So we're saying we're going to give you an image, that 100 etc.jpg file, which we know is going on a straight, and then we're saying, right, that computer vision library, read that file, resize the file to a size that our model is expecting, and this is an important step. So if that model was trained with an image of 500 by 500 pixels and we give it an image of 160 by 120, it's not going to work. So it's important to keep that in mind as well when you train your convolutional neural networks. These inputs dimensions must match. Okay, and then we're going to say show that image, rearrange the shape of that image array, which we've loaded here, and we're going to add the dimension. So it's going to be an array of three-dimensional arrays. And the reason we do this is because at training time, this is the same number of dimensions that's passed to the model. So this is what it's expecting. If we just pass the image to the model with 3 dimensions, it's going to throw an error. So, and then we say print the prediction, print the prediction, the 0th element of the prediction, because the prediction is actually going to give us a steering angle plus a throttle value. That's the way the model was trained, to output those 2 values. And finally, show us the steering angle that's in the JSON, so the ground truth steering angle. So we run this guy. I should have run it before I started talking, because the first prediction actually takes longer as it's compiling the, or something's happening in the background that's taking longer to run than the second prediction, for instance. So in the meantime, I'm going to jump over to this next cell, which is a pre-processing library. So this is something I actually used when I trained my models. And this is something that you've probably heard about if you've been taking your neurocomputing, machine learning, and other modules in any data science courses or in computing. You probably heard of this expression augmentation, augmenting data. And right, so I'll put that on pause and come back here. So what are we seeing here? We're seeing the prediction, and the prediction is an array with 2 elements. The first element is the unnormalized value of the steering, and the second value is the unnormalized value of the throttle. So it's telling me, and then this is the JSON array, and it says you are going fairly straight here. That's the ground truth. So it's telling me if I show this model to the image, the label is you're supposed to be driving straight, yet the model prediction saying, oh, you're supposed to be at minus 43 degrees steering. So this is a very hard left turn, bearing in mind that the Unity game engine could only output, because it's programmed to do so, a minimum of minus 25 degrees. So at this point, I figured, well, something's gone horribly wrong here, and that model is not doing very well. Anyway, on we go. So with what's the image augmentation? So I used a part of this library to pre-process the image. So when I trained that model, I was actually pre-processing it. So I was cropping the image, getting only bits of the road, so taking the sky out. And then I was converting it from RGB to YUV. So it's a so-called noisy, I forget the expression, but basically it's going to reduce the definition of the image as if you were squinting trying to look at this image. So we're going to run this guy just to load the augmentation library, and then we're going to run this number 10, and basically that's going to run another prediction, but running with the augmentation in this case. And this is only a subset of the augmentation actually used in the dissertation. So we could fit this in an hour, but the bit we're interested is this cropping bit and the RGB to YUV. So you lose. It's a lossy compression algorithm. That's the term I was looking for. So in DSP, that's what they would call it, or in computer vision, a lossy algorithm. So we're losing detail here. And it turns out that this works well with self-driving. So I'm just going to show some, where are we here? So I made a presentation here of, which I'm not going to go over, but self-driving obviously it has a long history. And when this DAVE competition came along, which is a DARPA autonomous vehicle competition, Ian Lecan and a group of collaborators, they created this model-sized vehicle that was driving around with using a convolutional neural network. And then later on in 2016, Bojarski and a group that's working at Intel did the same thing. And there's one guy that was working in both groups and actually had a correspondence with that guy as I was doing research for my dissertation, Ernst Miller. And there's the correspondence and the dissertation, and one of the appendixes, the guy was very helpful to say, yep, we did, this is how we did it, this is how we cropped it. So he gave me a few pointers in how the actual pre-processing happened. So, what we've seen here is with the pre-processing, it improved a little bit. So now it's telling us, right, you should be steering. Really, we want it to be steering straight, but all we can say at this point is if we're not pre-processing with this pre-trained model that you've loaded, you're getting minus 43. And if you do pre-process, you're getting minus 33, but it's still unusable. So we're going to run this. We're going to loop through all the files now and make a prediction for every image. So up to this point, we only predicted for one image. And here again, we predict for one image. Now we want to predict for every single image in our testing data sets. So what we've seen here, the ground truth, for which we've just plotted the labels basically, we're going to get all the images corresponding to these labels. And we're asking our model to say, go and give me a prediction, model.predict for that image. So what's happening here? It says there's a file mask, which is dataset-testing.jpg, where all the JPEG files are. We have a function, which was defined earlier on. Said go and get all the files. And then it says go through all the files and load it with the computer vision library, resize it, reshape it, predict it, save the prediction, but save the steering angle only. We're not interested in the throttle, and print prediction completed when the job is done. So there we go. And now we can plot the results. So we run this. And we see, right, this does not look very good because that's what it's telling us. And we've seen those weird results like negative 43 at 100, something like that. And we see, right, this does not look good. It doesn't even follow that pattern that we've seen here. So let's try the other one. Run predictions for images with pre-processing. And then same thing again, we're going to load all the files. And for every file, we're going to pre-process this time, which we didn't do in this step up here. There was no pre-processing. And then we are going to reshape the image, make the prediction, append again the steering angle only. So we use this, that's the way we index the 0th element of that array, of the prediction array, and append it to this list. So Ben, Max, how are we doing? Are we up to sell okay? Everything running okay?
Yeah.
Yeah, it's fine for me. Yeah.
Cool. Right. So we are going, after we've done this, after this finishes running, we're going to plot the results. So we should have at that point a prediction with pre-processing completed here. Next, we plot the results. So there's a note here. So this plot does follow the general trend of the ground truth. So if we think about what we were seeing here, we can say, okay, there is what seems like a right turn here. There is what seems like another right turn here, and a left turn, and a right turn, followed by a right turn, followed by a straight. But all the values are way negative. So this model is unusual, it's unusable, because we couldn't, if we generate a value that's less than the minimum our model could, well, you get the picture. It will constantly be steering hard left or very, very hard left or something in between. So anyway, now we need, so that's kind of a qualitative analysis. We're looking at the quality of that steer by looking at the plot, right? What about a quantitative analysis? And the quantitative analysis I used for the dissertation, I called goodness of steer. So how well or badly is my algorithm driving? So I'm going to just zoom in here a little bit. Where are we here? Oh, okay. So what this is doing, it's saying there's a function called G subscript S, goodness of steer, and it takes in two arguments, two arrays, a prediction and a ground truth array. Oops, what's going on? Let's try to shrink this a bit. Okay, so a prediction and a ground truth array. So it's going to do the sum as I goes from 1 to n, which is the number of examples, and take the absolute value of every prediction compared to every ground truth value. So, oh God, 60. And then it's going to divide it by n. And so basically it's taking an average of the absolute difference of the prediction and ground truth. Oops, I'll have to reset this. What's going on? My Zoom has gone a bit crazy. Okay, so, oops, thank God for that. Okay, so, oops. Basically what this is saying then is, yeah, it's the average of the absolute difference of predicted values and of the sum over the absolute values of the difference between prediction and ground truth. So if we run this guy, which is, if we run cell number 15, right, Max, I'm going to stop sharing a sec just to see if the screen stops going crazy, because I zoomed in here, and let's see if it fixes itself. And then could you hand it over to me again, or?
Yeah, sure. Let's try that.
Okay, so I'll stop that 1 sec.
Yeah, try it. Try it now.
Okay, so at this point, right, my screen is definitely going a bit crazy. So Ben, may I ask you to take over? If you can share your screen and carry on running from cell 15.
Sure. Shall I? I'll share my screen and then you can do the talking and I'll scroll.
Cool.
Would that work?
Yeah, that works.
All right.
I gave you the right.
Oh, thank you. All right. Can you see this?
Yeah.
Yes, perfect. Okay. So if you could run that cell that starts def GOS. So
Yeah.
what that is going to do is it says,
What it's waiting for here? Oh, it's extracting them again. Fine. I did run all on the cells.
okay. So
Fine. We don't need to run this one, do we?
that one, yes, we do. Well, in fact, do we? For completeness, I think it's best if we do.
Okay, so let's wait for that to catch up then and then talk through this one.
Okay, so right. Meantime, I'll just run through the, if you could maybe open a second tab.
For this notebook?
No, I just wanted to go, well, in fact, maybe we just wait. I don't know what you think. Should be a couple of minutes.
Yeah, it shouldn't be too long. Yeah.
Oh,
Okay,
so we're on
completed.
11 now. Okay, cool. So we should be running, 13. Cool, we're almost there.
Would GPU help here? What are we on? Oh, we're on GPU. Okay, fine.
Yeah, it seems to default to GPU now.
Okay.
Well, since you gave me that tip, and I've noticed, I don't know if Google picked it up via phone and said, okay, yeah, leave it to me. But every time I've been using it, it's defaulted to GPU. Right. In the meantime, has anyone got any questions? Yes. So Daniel, this is an extract from my actual dissertation submission. And in the page we started, which is linked in the chat. So in the GitHub page, there's a link to a set of slides, 25 slides, which are my dissertation. There's a link to the dissertation itself, which is a bit long-winded, but there's some sections in the results that I think kind of summarize what was found. And then there's the link to the LaTeX files that were used to format dissertation, in case anyone's stuck for formatting your MSc dissertation or any dissertation. So those 3 links are provided at that GitHub page.
We're ready when you are, Daniel, on this, I think.
Oh, so on that, so what this is telling us is that goodness of steer value, and the name was a bit unfortunate. I made a note of this in my dissertation because the actual lower value is better. So, but then there's a suggestion how to fix that in the dissertation. But what we're seeing here is that the lower value is the best. So what this is saying is the one with pre-processing gave us a slightly better result. And it said on average, you're 35 degrees off where you should be, which is, I would say, very bad. All right. So next, we're going to run this next cell. And if you run that one, we're going to run all the plots with an overlay. So we define the function here, and then we should be seeing these 3 plots overlaid on the screen. So in blue, it's the one with no processing, where the goodness of steer was 42.55, and the unit here is degrees. The one in orange with pre-processing, which in a previous plot looked very close to closer to what the actual track steering was supposed to be. So that's the one plotted in orange. The goodness of steer is 35.64 degrees. but it's flattened, and the reason why is that the highest and lowest values kind of compress it because it's somewhere in between. So the super low values and no pre-processing and the higher values in the ground truth kind of compress the orange line. So it starts looking nothing like, or almost nothing like the, where are we? Okay, we've jumped a bit. Can we go back a little bit?
Yeah, it just ran again, and now it's giving me a slightly different output.
Oh, okay. All right, cool. So,
should we move on? Should we go to train model?
Yeah, let's go. So, so then if you go with that one, so basically it didn't work. And I was thinking, why didn't it work? Why couldn't I replicate the results here? Well, so be it. Let's train a model. So there's a big section of code that's doing exactly that. And if you've been in a previous session, or if you're doing neural computing or machine learning in your MSc, this code should be familiar. So basically we're loading all the familiar TensorFlow, Keras libraries. And the bit that's different here is that because it is a regression task, we're not using that scheme that's very often used in Keras, or always used as far as I know, which is your label data is in a folder and that the data in the label, the folder name is a label. So that's used a lot in Keras. But in this case, because it's a regression task and we can't really group a bunch of images in a single folder by a steering angle because they all differ, it's a continuous value. And then the scheme to actually prepare a data is slightly different. All right, so we can move on. And we see that we ran it for 10 epochs, and around epoch 5, it was fairly close to optimal already. So what's that saying is, well, 10 is enough. Like we can get this running for 100 epochs and beyond, but we got very close to optimal after about 5. Okay, so now in that code, we actually save the model in the next cell. Oh, yes, and there's the loss and accuracy in training and testing validation, loss and accuracy. There's a whole discussion around that and overfitting, which I'm not going to cover at this point. So we're going now to load the model. So what we did there was we listed everything that's on the file system now, and it's saying on the file system now we have adc.json, which we had before, this model that we've just saved, ai-av-model.h5, the models directory, the sample data directory, the data set that we downloaded, the data set itself, in an NVIDIA one folder. Okay, and that was created by the previous step. So next we start again, we're going to predict with no pre-processing. So in this case, the model we just trained was not trained with pre-processing. So the expectation is that in this case, we're going to get better results with no pre-processing than with pre-processing. And the model that we loaded, so the pre-trained model was trained with pre-processing. In that case, we got a slightly better result with pre-processing. So we got a better, this is going by the quantitative analysis. So the metric that was used, goodness of steer, showed that in the previous model with the pre-processing, we got a better result. So we'll run this, and just to recap what the code is doing, we're loading a file mask called data, and the file mask is a string. And then we're getting the files, we're creating an empty list, we're looping through all the files, we're loading them with the computer vision library, CV2, we're reshaping it, resizing the image, reshaping the array, passing the reshaped array to the predict function, and we're getting a prediction. And then we're appending only the steering angle. We're not worrying about the throttle. So that's completed. Now we're going to plot those results. So if you run the next cell, so the plot results cell, so what we're doing here is so if we look at this, saying, right, that's not looking too bad now. So if we, because it's kind of, we start with 0 and then we go, so we can see clearly it's that pattern, and it's pretty much starts at 0 degrees, ends at 0 degrees. So this is looking promising now. It looks like this guy is actually doing a better job than before. Right, let's move on to the next one and see what about predicting with no pre-processing. So, and if, so continuing, so this time, if for every file, so we've loaded the files with using this get JPEG file. We initialized an empty list. We're gonna do a for loop. And for every file, which is a path in files, so files is a list of strings. Every string corresponds to an image path. For every file in that list of paths, we are going to run it through the pre-process function, which we defined earlier on. And what that's going to do is load this file, loads the image from given by that file path, resize it, and then crop the top, crop the bottom, move it from RGB to YUV space, and finally make the prediction, save the steering angle. So if we run this guy now, we say, okay, so yeah, if you could run that spin just to make sure it did run, because we're actually going to need that array. Okay, so now we see, right, this one is not doing a very good job, but the steering angles are not as crazy as they were before. So let's run this next cell to do some quantitative analysis. And it says, right, the steering angle with no pre-processing was 2.05 degrees, which is a lot better than the previous one. And with pre-processing, 5.24. If we overlay these guys now, so we're going to run this cell 24, and we say, right, what happened here is, so the yellow plot are the predictions with pre-processing. So we can see the label there on the bottom right of the plot, and it says the goodness of steer was 5.24. Now it got squashed again because the interval is close around 4, and the lowest value of the highest value of the ground truth is near 25, and the lowest value is around -5. So it keeps the scale. So that one is well represented, but the orange plots get squashed. And if we scroll up a little bit at the previous plot, that was the plot that represents the orange plot in the next one. And if we look at the y-axis, it goes from 3.5 to 5. So if we scroll down again, and we say, right, where is 3.5 and 5? And say, that's the reason it's got squashed, right? Because it's a tiny interval in this graph. Mm-hmm. Cool. So with no pre-processing, okay, so the question from Daniel is, did I decide on goodness of steer metric, or did that come from the literature? I decided on that, and that was like one of the, one of the deliverables in my dissertation. It was like, well, I have to get this game engine running, be able to add the noise, and decide on a metric. And the metric was decided, and in hindsight, it looks fairly obvious, right? Well, take the average of the steering angle error of the absolute value, because depending on which way it's going, it could cancel out each other and look really good. So just this absolute value was the main, I would say, non-intuitive thing in the goodness of steer. So in answer to your question, yeah, I did work that out myself, but I imagine that other people use similar schemes for other problems. So if we look now at these plots again, the one that was with no pre-processing, and remember, we did not pre-process the images, we just showed them as they were to the model when we trained them this on Google Colab on this last section. When we actually trained our own model, it looks kind of usable because the line is following kind of closely. The blue line is following the green line. Now, one more observation about these peaks and troughs as the simulated vehicle is going around a bend. So this first right turn, you can see it seems to be shifting wildly between like left and right steering as it's going around the right turn. And what I wrote in the dissertation is this could be attributed to the PID algorithm. So this proportional integrate derivative, basically on the game engine, the car is trying to keep to a path, but in the game engine, the car is ruled by physics, by laws of physics. So it's traveling along. There's a physics engine within within Unity and every game engine, or at least the two ones I know. And as it's going around, it starts drifting from the path where it should be, from the road. So the PID says, no, you need to go back. So it tries going back. And then if it drifts the other way, it says, no, go back the other way. And we see that if it's going around a bend, like when it takes these 4 right turns and the left turns, that's when there's the most kind of crazy steering, I would say, because that's when the most corrections need to be applied by this algorithm to keep the car on track. And when it goes straight, well, there's hardly any correcting to be done. So that's how I explained those crazy zigzag patterns as it's negotiating the turns. So if we look at the blue line, which did quite well there, we see that it takes those turns quite smoothly. So that first right turn, it steers to the right, and then it pretty much holds the steering at close to 10 degrees for the entire turn, and then it starts going back to 0 degrees, oversteers a little bit, and then comes back, and then there's another right turn. When it takes that long left turn, which is that hump almost in the middle of the plots, we can see that also it's very smooth. So it takes, once it's on that left turn, it holds the steering about 3 degrees throughout the turn. And that was very interesting to see that the model seemed to be driving okay. And so recapping on what we've done so far, we used the pre-trained TensorFlow Keras model, and we also trained the model. So originally, the idea was only to use pre-trained model. But when I actually plotted them, I was quite shocked that it was not doing well on, and I said, wow, we've advertised this workshop already, best get some more interesting results. So, so then we went on to train one here online. And then, so Ben, if you could scroll down again to the end, please. So, and then we predicted steering angles given a set of images going around that track that we showed earlier in GitHub. So there was that image of a track, and the track itself was generated by the Unity game engine using an environment called SD Sandbox. So I borrowed this environment, who was developed by someone else. It's also on GitHub, and I've put some links around the code. So when we did our own training, our own model, I put a link to this SD Sandbox where I borrowed heavily from this code for my own dissertation. This is known. So what we did here is done as a regression task, because we're predicting a continuous value, in this case, a steering angle, as opposed to a classification task, which is what we've done before. So in previous workshops, we had two sets of images, fire and no fire. And then we wanted to predict, does this image contain fire? And then in another workshop, we had a set of audio files, and a set of audio files that were the word yes, and another that were the word no. And then our algorithm was, why did I choose absolute error over squared error? Well, this is basically that helps to keep the values lower. So if I square those errors, I'd say, right, okay, I'm squaring the errors. I'm not, so the question there was, why did I choose absolute value over squared? Why did I choose the absolute error over the squared error? So I could take that and square so another option, so just a pause here on what we're talking about. So let's say we have a predicted angle and a ground truth angle. Let's say we take the difference and then we square that difference. And then that number is starting to increase and increase and increase. And then so I figured, is there a need to increase that number? So let's say you have a track that instead of 1400 frames has 25,000 frames, which may be the case. Was there any gain to be had between squaring and taking the absolute value? And I figured, you know what, if I take the absolute value, I'm going to keep those numbers lower. So that was, as far as I remember, in my mind, the justification for using absolute values. But, I'm open to discussion, and if anyone has any suggestions in any metrics, I'd be happy to hear that, because I want to take this research further. So yeah, by all means, let's continue that, take that discussion offline. So next thing, the same image size used in training must be used at inference time for predicting. So if you're training your model, and then when the time comes to predict, you need to be aware of the geometry of the image. And then finally, so said, okay, we trained this here, and that's a bit of the self-driving, but how do we actually go that step further and implement this on hardware? So there's a community out there called DIY Robocars, and where this is one of the platforms, SD Sandbox, of which I borrowed a lot of code, used to train these cars. So you could get this model, run it on a Raspberry Pi, then get your robocar to go around a track, and some work better than others. The only thing to keep in mind is that you need the appropriate track data set. So most of these guys from DIY Robocars, they're using a so-called warehouse track. So it's a known track. They have their lane markings, and I've got an image of these guys in the slides. So in the GitHub, we have some slides. There's a link there for slides. And there are 25 slides about the dissertation itself. So if anyone's interested in having a further look in those slides, I think they're pretty self-explanatory. And at this point, I think that's everything we had to cover. Thanks for taking part and turning up. And finally, does anyone have any questions? Okay, so the GitHub link, Ben, could you be would you be able to share? Okay, sure. So the question from Daniel is how would that choice come about, right? And Daniel, the answer is I spoke to a total of 4 companies looking for an internship that had something to do with embedded software, and which is what I work with, and machine learning. And every company told me the same thing. Well, we're very interested, but we haven't got the data to give you. And the data was always a stumbling block. So I went to Artur Garces, which is one which you're probably familiar with. So neurocomputing, machine learning. And I said, Artur, have you got a topic for a dissertation that could be a good hook for a PhD studentship program that's happening? This is going back 1 year. So there's a PhD studentship program sponsored by Intel called Safety and Autonomous Vehicle Safety. So that's the theme. And I said, have you got a theme that's a good hook for that PhD studentship? And he said, yes. The theme he gave me was evaluation of self-driving cars using CNNs in the rain. And here I am. So that's how it happened. So basically, I asked one of the potential supervisors for a topic. Yep, no problem. Yep.
And the plan is, Daniel, is it to take this forward for the PhD topic?
Okay, so I've applied for a PhD. So I've sent in an application and I've written a proposal, which was, if anyone's interested in doing a PhD, I'll tell you this thing. There are a few going around City and other places, and it's probably the easiest thing you'll write during your entire, a lot easier than anything you write in your MSc, because it's 3 pages, and compared to dissertation, a lot of the coursework we had, I would say it's pretty easy. The main thing is finding a supervisor, finding the research that you're interested in, and that's it. But that's what ideally what I'd like to do now, take the research forward. And then, so the suggested topic for the PhD is evaluation of self-driving cars using deep networks in complex traffic systems. So basically, we're adding more deep networks, not only convolutional networks, transformers, reinforcement learning, and also more complex traffic systems like traffic lights, vehicles, pedestrians, push bikes. And this would all be coming via another environment called Carla, C-A-R-L-A, which is based on the Unreal Engine and is currently being used by Udacity for their self-learning autonomous vehicle engineer course. So that's the story so far.
Exciting stuff. Yeah. When will you hear back if it's going ahead or not? What's the time frame?
The time frame is, it's supposed to start in September. So I would expect any time between now and a little bit before September, if things go okay. But, there's still like the ambition to publish the results. So I'm in touch with Artur, my supervisor, and then we're kind of having that discussion, how maybe get this published on arXiv, so RAXIV, if you're not familiar with arXiv.org. So a lot of preprint stuff gets printed there. So if not printed in a peer-reviewed journal, maybe try to get it on arXiv and show the results, of which a few are discussed in the PDF. On GitHub, there's a link to the slides, and at the end, there's some the conclusions and suggestions for future work. So the idea would be get that stuff, try to make an article out of it.
Cool.
Nice.
All right. Any other questions for Daniel?
The recordings of these sessions, right? They'll be online soon. So Ben, I'll hand this over to you and Maxim to field.
Yeah. Also, this should be a link for our YouTube channel. So feel free to check that for previous sessions. Also, Daniel already have done a few sessions with us few sessions ago, so you can check his past sessions as well if you're interested, and keep updated for the new session. It's going to be posted here.
Yeah, we'll post it in the next sort of day or so pretty soon, and then we'll put it in the data science group chat. So if you're not part of that group chat, it's where we normally post lots of our updates and things. Would you be able to put a link in the chat as well, Max, for that?
Yeah, give me a second.
Awesome. Okay.
Yeah, and also, Daniel, if people want to reach you, what would be the best way to do it?
there's if you go on my GitHub, which is github.com, DSIKAR, you can ping me that way, or on my city email address, daniel.sikar@city.act.uk, or in the WhatsApp chat. So Ben or Max are gonna put the link there, so we're in the chat. So if anyone wants to ping us that way, or in the MSC WhatsApp group. So any of those channels, on Twitter. So
Actually, Ben, can you do the invite? I think I'm not the admin for that group.
Oh yeah, sure, that's fine. I'll do that. Cool.
Yeah, and again, thank you everyone for joining us this session. And stay tuned for
if anyone's going to be still at the university next year, then you can apply for a position in the society.
Yeah.
Which is what we're doing. Okay, I'll find the link. There we go.
Yeah. Thank you again, everyone. We'll just wait for the group chat link. Yeah. Should be this one. Yeah, and I believe that's all for today's session.
All right. Yeah. Thanks everyone for coming.
Yeah, and thank you, Daniel, for preparing it and running.
Yeah, thanks, Daniel. Appreciate it.
yeah, thanks guys for organizing, from Data Science Society, Ben and Max. And thanks everyone for coming, and hope to see you guys around soon. Hopefully a few of you running it, and Ben's also doing an MSc in AI, so hopefully he'll be back soon running a Jupyter notebook or two.
Hopefully, yeah, sounds good.
Yeah.
Okay.
That'd be fun. All right.
All right. Well, see everyone.
Cheers.
Bye.
All right, we'll end it there. Thanks everyone. Bye-bye.
Yes, bye-bye.